Okay, welcome back. Um, we're now going to look at section 17.4, which ties up line integrals with double integrals. It circles back to our double integrals in chapter 16. And this is the section on Green's theorem. Before we dive into the theorem itself, let's go way back to the del operator we first saw in computing the gradients in chapter 15, and the project 1 that we did in analyzing the curl and divergence that are directly related algebraically to that gradient. So in Cartesian, the curl is a vector for 2 dimensions that is the difference of the x and y component. If we expanded this out into 3 dimensions, you would have 3 different three different differences of mixed partials. And we saw this show up in the test for a conservative field. But just in 2D, we have this form of the curl, just the k component. The divergence of a field, the dot product with nabla instead of the cross product, del operator, I called it nabla, that's the name of the shape, the Jewish harp. Sorry, the harp, whatever it is. The dot product gives us f sub x plus g sub y. And so we can think of the dot product, or sorry, the divergence as the sum of the aligned variables, like the x partial of the x component plus the y partial of the y component, whereas the curl is the mixed partials, the difference of the mixed partials, the x partial of the y component minus the y partial of the x component. And the curl is a vector giving rotation about a certain axis. K hat is the axis, is the normal vector to the rotations in the xy plane, whereas divergence is a scalar, a measurement. In polar, we represent our fields in terms of some amount going in the radial direction, either out or in, and then some amount going around counterclockwise, either counterclockwise positive or clockwise negative. And we saw with the gradient form, we had this theta partial over r, and so we group a term n that is over r to kind of quantify some important piece. And then when we computed the curl in polar, we got the similar differences of the mixed partials, n sub r minus m sub theta, again the r partial of the theta component minus the theta partial of the r component, all divided by a common r. And that is the k hat direction. So again, this is rotation in the x, y, or r theta plane, perpendicular to that z-axis. And divergence expands out. This one I did a video on, just to, you should review that to see how the divergence is converted into polar, because in both of these, we have to be taking the r and theta partials of the directions, the radial direction and the angular direction, that are changing with theta, with respect to theta. And so we get the sum of the r partial of m, again, m is the r component, so it makes sense, plus m over r, and that comes from a product rule, and then n sub theta, the theta partial of the theta component, divided by r squared. Okay, so now let's dive into the Green's theorem and see how we can utilize this idea of divergence and curl in that. Okay, so Move this around just a little bit here. Let C be a simple closed piecewise smooth curve. Okay, okay. So close. There you go, now it's close. Okay, so that's our piecewise smooth curve. We know that this is moving counterclockwise, so there's our unit tangent vector. And it is piecewise smooth, which means that there may be some places like here where maybe there's some sharp cusps, but it should be differentiable. Oh. Should be differentiable in between all those places. So piecewise smooth means you could break it into a number of pieces, each of which is infinitely differentiable. It's an oriented curve, that's oriented counterclockwise, and then it encloses a connected and simply connected region R. So here is R. If the components of the vector field have continuous first partial derivatives, then the following two statements are true. First statement, if we measure the circulation or the work done all the way around the boundary, this circulation is the macroscopic sum of the infinitesimal circulations called curls. And the curl is defined by, as we saw before, the del operator crossed with the vector field, all dotted with, in this case, k hat. That's the perpendicular vector to the plane. So all of our curls will be perpendicular, will be measures of rotation perpendicular to the plane. And what we're doing here there we go. So we measure the curl as this quantity of del operator cross F, but then we dot it with k hat to extract out how much of the rotation is happening in the plane. So that's that dotted with k hat is not part of the curl definition. It's actually part of how we measure that curl in the double integral. Back a little bit. Okay. So to think about this, let me draw some pictures, some little curls. So this theorem says that if we measure the curl at every single point and we get numerical values, we add up all those numerical values, we will get a total which is equal to the line integral around the boundary. What's that? What that is saying is that the information contained inside the region in terms of the curl, the information contained inside the region in the curls, these little rotations, is the same as the information accumulated by measuring the work done to go around the outside of the region. There is a balance between information we can measure on the boundary and information we can measure in the interior. They are equal as long as the things you measure are carefully selected. If you measure the curls inside, you'll get the same amount as measuring the field aligned with your direction, capital T. So there we go. So if you measure how much the field is aligned with your direction of motion on the curve going around, that is the same thing as adding up all the little curls, little bits of rotation that are in the plane or perpendicular to k hat. Okay, now notice that the theorem said we needed to have a connected and simply connected region. Well, connected just means one piece. Simply connected means there's no holes. And sometimes we've mentioned that there could be a hole punched through this. And if so, we have to surgically cut in. And then, instead of our unit tangent vector pointing counterclockwise, it comes in goes around and then exits back. And so if there's any hole inside, what we have to do is basically cut your one region into create a line cut through, so that instead of having a hole, you just go around that hole and meet, kind of sewing those two pieces together, not necessarily so they're the same, but so that there's no area missing in between them. And so that's how we fix a problem that has a hole in it, that if there's a hole, we try to cut through, we can break it up, but then you say, well, it has to be connected. Well, it's okay, as long as those two edges are right next to each other. Well, let's see how this idea works out in the second form of Green's theorem, the flux form. The first one is the circulation or work form. This is the flux form. Again, circulation is work done all the way around. There's no fancy word for flux, except flux is usually measured all the way across a boundary, and if we only do a part of the flux, we usually call it a partial flux. So I guess there's like work and circulation and partial flux and flux. It's not very tidy, is it? Okay, it's what we have. The flux outward across the boundary is the macroscopic sum of the infinitesimal flux pieces called divergence at each point. And that divergence is described by the dot product of the del operator and the vector field. So again, we'll draw what the divergence looks like. And so basically we take this kind of purple detector and we put it over each point to see if there's a positive or negative amount of pushing away. And if we measure this amount of divergence at every single point inside the region, we will get a total that is equal to the amount that the vector field pushes across the boundary. So I'll just draw this normal vector. As we go inside, our normal vector switches and points in. And so our normal vector is always pointing out of the region. And if there's a hole, it'll point into that hole. And so what we're asking is, how much is this vector field pushing out of the region, either out, away, out on the outside boundary, or pushing in to some hole inside the region? And we can either measure this quantity along the entire boundary, or we could measure it by adding up all the little divergences. So this is equating this idea of taking the divergence of a field, which often will simplify it down by differentiation, versus dotting it with a normal. Okay, so that is the idea behind Green's theorem. We'll wait to do the proof a little bit later. It's a little bit involved, but I wanted to give you some examples to see how this idea is utilized. Here's some examples. So here's one example. We are computing the circulation around an annulus bounded by two circles of radius 1 and 2 for this function. Interesting looking function. Vector field, I don't know what it looks like, but you know what, we'll go ahead and analyze it given what we know. Let's try drawing this shape. Make sure we have the draw. There it is. It says there are two circles. Okay. There's one circle, so that's circle radius 2. And then we have also a circle of radius 1 on the inside. Okay, so let's look at our curve. We want to travel around it and measure circulation. So there's our t. Moving us orientation. We're going to have to cut in and go opposite direction on the inside piece of the annulus. And so that's the idea. We're trying to measure that circulation. And we're going to do it by looking at the area of this annulus, or at least integrating over the area, that region. So let me color in the region we are integrating. There we go. Something like that. Okay. There you go, smiley face. Okay, so once we have those pieces in mind, we're looking at an F and a G. I want to compute the curl using G sub x minus F sub y. And so we look at F and, G, and the x partial of G just gives us a 1 from the x and 0 from the y term. And so that's where this 1 comes in. And then F sub y is a -1, so there we go. Take 1 minus a -1, that gives us 2. So that's the thing that we're integrating. Notice that when we plug it in, we have our vector of this amount to k hat. We dot it with k hat, meaning that we get all of the z components. You can think of it another way. K hat is a unit vector, so it dotted with itself is 1. And then we rewrite dA, or I should say convert dA into polar, r dr d theta, and integrate from 0 to 2 pi and 1 to 2. Now, we didn't convert the vector field into polar. We just converted the double integral. Why? Are you not seeing what I'm seeing? It's 2 circles, right? It's 2 circles. Why would you integrate that in any other way? Like it's absurd. You have to use polar. Okay, you don't have to. But just think about how nasty this is in Cartesian. Not only are you integrating over this weird curved surface, but you have multiple different upper and lower curves based upon where it sits. I mean, it's just a mess, right? So it's obvious that we want to use polar for the double integral. Okay. So we do it. We integrate r to r, we get an r squared. Pull the d theta part out, that's your 2 pi. And then r squared evaluated at 2 is 4, at 1 is 1. Subtract, we get 3. So multiplying together, boom, 6 pi. Now, there are 2 things important here. 1, it's not 0. And 2, it's positive. So the circulation being positive means that this particular vector field is helpful in moving us along. And you may think, well, of course it's helpful in moving us around this curve, because if you look a little closer, right there and right there, it has a rotation component in it. So we could group that out over here, and what's left over is a radial component. And so we could say that this is this vector is pointing counterclockwise because it's following that negative y-axis pattern we see in the angular direction theta hat. And for the radial component, it's pointing inward. And if we want to be even more careful, we can divide by r and multiply r correspondingly to write this in terms of the radial and angular unit vectors. And we see that not only is it pointing inward and pointing counterclockwise, but that the vectors for the vector field f grow with distance. Let me try drawing these a little bit. They're pointing a little bit, they're pointing counterclockwise and in. So something, let me see. Can you see that? Yeah. And as we go in, they get smaller. As you go out, they get bigger. So let's do a few more. Like that. And the question now is, does this still make sense that our circulation all the way around is positive? Because if I look on the inside, my orange arrows are going opposite of my blue arrows. Whereas at the outer edges, they're going more or less with it. So I can think of at the beginning of my curve on this part, the blue vector fields are helping me push along this way, this path, this circular path. But as I cut in and then go the opposite direction, they're opposing me, or the angle is obtuse in a sense, all the way around. But if you look closer, the vectors on the outer edge are bigger. And so you basically get, you can think of it as if you're riding like a roller coaster, you pick up speed here or gain momentum there because there's a dramatic positive amount of work. And then when you switch over and going backwards against the flow, that friction is not as strong of a force as the propellant force was going around the outside. So because the vector field is stronger as you go farther away, the push on the outer edge is greater than the pull back on the inner edge or the interior curve. Whew. Okay, so let me undo. No, I'll leave that picture there. Let me erase a few of the other pictures as we move on. I'll clear them. I will erase quite a bit actually, because that is the problem. We're done. We solved it, and we thought about it, and we talked about it, and we drew pictures. So let's erase this lovely work and move on to another problem. I think it's helpful for us to see this same or a similar problem like this in polar coordinates, because there is can I get just oops, Just the light blue. Okay, there you go. So now let's look at a similar problem. Make some space. Okay, so a similar problem where we're computing now the flux out of the annulus bounded by the circles of radius 1 and 2. So in this case, we're looking at how much of that not going to get it. I'm going to leave it. I'll leave it. How much of this new vector field leaves our blue region? So I'll draw the arrows again. Try that again. Getting them perpendicular to my tangent vectors. And as we go inside, they follow the right-hand rule and point inward instead of outward. Okay, now this this field is a little bit different. For one, it's a lot more complicated than we had to deal with before. So this is going to be nasty to do in Cartesian. But we already know that the first one could be turned into polar, and this one looks very similar. The numerator, in fact, is identical. Just the denominator has changed. There is a denominator now, and it's just powers of r. So this can definitely be translated into polar. We know that the region is well defined in polar. Let's just go all the way into polar. So yeah, immediately simplify into polar. We have our two pieces, a radial piece, and the x component in the x direction, y component y direction. Again, they're the same coefficients. Very nice. Pull that out. We have 3 copies of the radius in the bottom. We need 1 for a unit vector, and so we have 2 left over. So there's their m term. And then for theta, we have a 1 over r squared, which if I factor an r out of the denominator, I get a 1 over r as my n, my theta partial of p if it existed. And then finally, I will use the identity that we talked about at the beginning from project 1, transferring the divergence into polar. So let's compute the flux. We're going to plug in our m and n components, there they are, in for these pieces in the formula. And so for m, I take the derivative, that spits out a -2 and reduces down to a -3 power. There we go. And then m over r is a similar power here, opposite sign there, combined together. And then n sub theta, n doesn't depend upon theta, so n sub theta is 0 here. So we combine our terms together, we get a nice +2 over r cubed. Remember that we have another r from the Jacobian of working in polar coordinates for the double integral. And so we get the integral of 2 r to the -2 power 2 pi is what we get from integrating in terms of theta. Again, there's no theta, so whoosh, just pull that 2 pi out. And integrating through, we get a negative. We evaluate, we get a negative 1/2 multiplied by our negative 4 pi, and that gives us a 2 pi. Oh no, this is weird, because when we drew the vector field last time, we saw that it was obviously pointing inward, and this one is still pointing inward, crossing in. But now it's telling us that our overall flux is positive. It's outward. It's out of the region. So let's do a quick sketch of our vector field again. This time, we notice that dividing by r squared means that it'll decrease with distance. So I'm drawing the arrows a little bit more dramatically, perhaps in the middle. But again, they're pointing inward, and they're much smaller as we go farther out. They dramatically decrease. And we can see that the movement out of the region into the middle is very strong based upon the blue arrows of the vector field. The vector field is ejecting particles into the middle in a very strong fashion, and it's only pulling particles in from the outside with a very weak amount of force. So when you compare those two, it has an overall positive flux because, make a note of that, overall positive flux because the amount of partial flux that's out of the region and the inside is greater than the amount of negative flux coming in from the outer edge. So the overall flux is positive. Okay, let me just take a look at a graph of this field just to verify our intuition and my sketch here to see I'm not just making this stuff up, but I'm actually fairly close to what it really looks like. So let's switch over. Here we go. This is a color coordinated version of the showing the strength of the vector fields. And you notice that it's really only strong right near that center, and it just grays out very, very quickly. Now, what's cool about this app, this is by Falstad, is that you can animate it. So let's throw some particles on there that are following these paths. Okay, and let it go. And now you can see how that slow pull in on the exterior is far outweighed by the ejection of particles into towards the center. If I were to, I'll pause that real quick. Let me draw some circle on here, some circles, just so we can compare. There's one circle. Okay, so imagine that that's r equals 1, r equals 2, r equals 1, r equals 2. I don't have a scale drawn on here, so we're going to have to just go with it. And let's run it again. You can see the slow moving work that's coming over here on the outside is very slow. That's the negative flux pulling in, but then it's ejecting very quickly in the direct center right there. Like that. Okay, let's stop that. Boop. Now, what you can also do with this app is change your own, modify it to have your own vector fields. Notice that I'm under the setup user defined field option that's on the very, very, very bottom there. And I've used sqrt to represent the square root function with nice round parentheses. That will utilize the square root function. I've had a couple of issues with trying to modify the syntax, but it's just sqrt and then parentheses. I'll activate it. One other thing is that I ran into is that you can't have like a 2x in here. It doesn't understand that, but a 2 times an x it understands. Basically, you have to have the operation between any variables or constants. And if we wanted, we could turn that vector field into a force vector field to see how these could describe accelerations instead of just velocities. And it looks like there are some errors where it's shooting out past it, which is kind of interesting. It's accelerating so fast in the center that it's ejecting particles. So we'll keep it a little bit simpler with our velocity field. It's a little bit easier to keep track of. And then we're thinking of it in terms of fluid flow in that case. One other thing that you can do is look at some curl detectors. And this will give you, instead of dots, it'll give you little X's with a knob on one end that you can think of as a floating pair of sticks, and you want to see if they're rotated in space. So as they move, are they being rotated? Is there some rotation of these particles? Now they're getting pulled in so fast to the center that's kind of hard to see that they are turning, they are curling around a bit, and the curl is quite dramatic right in the interior region right there. You can slow it down a bit if you want. And then you can go back to the vector field, which seems rather boring after all this, right? But just seeing the strength based upon the coloration of those pieces. Okay, so that gives the main examples demonstrating the Green's theorem.